So the scientific approach to knowledge. Scientists use an empirical approach. Empirical means it's based on observation and experiment. And this is in contrast to a philosophical approach where you sit and think about things. So what we call the scientific method is a process for understanding nature. We observe nature, we observe its behavior, and we come up with ideas about nature, and then we test those ideas. And this is how we learn about the universe around us. So key characteristics are observation. Let's see if I can find my highlighter. So we've got observation, formulation of hypotheses, experimentation, and then the formulation of laws and theories. So I've got a video here. Hopefully it'll run. That's not a good sign. That's the spinning pinwheel of death. Okay. It's a video about the scientific method. That's some hokey music and there's no words. So there's this guy sitting and he's chilling to some music and reading a book. And he's got some plants. And he sees that this plant is tall and this other plant is not as tall. And he's wondering, what's up with this? That's his observation. So he's measuring, observing, making notes. And from his observation, he comes up with a hypothesis. Why is the one plant taller than the other plant? He comes up with some ideas. And does an experiment. It's great to have an idea of why the plant's taller, but you have to actually test it to see if your idea is correct. So his first hypothesis is that reading the book to the plants will cause them to grow. So he's got two plants and he's reading to one and he's not reading to the other and he's measuring them. He's performing an experiment. Science can be tedious. This is taking a whole month. Other hypothesis had to do with music. So we're going to play music for one plant and not for the other. See if that affects how fast they grow. The third hypothesis has to do with the amount of light. So this plant is next to an open window, getting lots of sunlight. And this plant is next to a window that has the blinds closed. And so I'm going to measure these plants over the course of the month and see what happens. He's got two plants because all plants grow regardless of, what you're doing to them. And so to compare and see if the sunlight is having an effect, you have to compare it to one that doesn't have the sunlight. So now he's got some results from his experiments. And these are going to either support or refute the hypotheses. So test 1, no effect. Music, no effect. But the sunlight does offer an explanation of why the one plant grew faster than the other. It's kind of a cool video because it doesn't matter what language you speak, you could still understand it. So keep that in mind as we talk about the scientific method. So observations. Observations are also known as data. Data is something you can observe. So the observation there that the person had was that the one plant was taller than the other plant, and that can be measured. So you would measure it and write it down. Descriptions about the characteristics or behavior of nature. Now, an example in your text was from a scientist named Antoine Lavoisier, lived back in the 1700s. I am not going to test you on the history of chemistry, okay? So I'm going to give you some names here and some dates. I'm not going to test you on them. I think it's important that you have heard that these people exist and have a clue as to how long ago some of these things happened. Back in the 1700s, this guy was fascinated with burning stuff. Anybody in here like to burn stuff? A little secret pyromaniac? Yeah, I think all chemists are secret pyromaniacs. It's just fun. I'm not into things that are dangerous, but I love a good small contained fire. So he made careful measurements of the mass of objects before and after burning them. Now, I think we've all observed a piece of wood burning either in a campfire or a fireplace, right? You put this big piece of wood in there, you have your fire, and then afterward, are the ashes that are left as heavy as the piece of wood was? No, there's a significant change in the wood, right? So what Lavoisier did is he burned things in closed containers, not open to the atmosphere. And what he observed is that there was no change in the total mass of the container from before and after burning. So this was an observation. And the observation often leads to a hypothesis. As we observe, okay, this is what happened, and then we want to know why. Why? Why is the one plant taller than the other plant? Just, we're curious. So the observation leads to a hypothesis. A hypothesis is a tentative interpretation or explanation. We're not saying that this is true, but we're saying, I think this is why this observation happened. So Lavoisier explained his observations of burning things by hypothesizing that when a substance burns, it combines with a component of the air. And, ultimately he ended up getting it right, but his initial ideas were a little strange. He named this substance phlogiston, and you could read all about that on Wikipedia if you're interested. What's important about a hypothesis is it needs to be testable. It has to be something you can test. It has to be falsifiable, okay? If you come up with an idea that can't possibly be tested, well, maybe it's correct, but maybe it isn't, and there's no way of knowing, and so it's not very useful. Yeah, I can't do that. So we test hypotheses using experiments. Experiments are highly controlled procedures designed to generate observation. So in the video, we had an example. There were 3 hypotheses, and so there were 3 different experiments that were done. One was one hypothesis was the process of reading next to this plant is causing it to grow faster than the other plant. So it's a highly controlled procedure. Here's my friend the train. I think there's one more. No? Is he done? I think he's done. Okay. So he had one plant that he read books to and another plant he didn't. So he has a control. I did one thing to this and I didn't do it to the other, so we can see if that's making a difference. He did that with the music and with the sunlight. Okay, then you look at the results. The results of the experiment may say, nope, your idea was crap, right? Reading a book to the plant made no difference. Well, is that experiment a failure? No. It did what it was supposed to do. It showed us, is the hypothesis correct? It says, no, it's not correct. Playing music to the plant did not appear to affect its growth. But giving one plant more sunlight than the other did cause a difference. And so that confirms the hypothesis that the sunlight is causing the plant to grow faster. So the results can support the hypothesis or they can prove it wrong. When a hypothesis is proven wrong, sometimes we just pitch it. Just, worthless. Not going to pursue that any farther. But sometimes what we just need to do is modify the hypothesis. Just change it a little bit, and then we test it again. This is a very circular process. So the results of the scientific method are scientific laws and scientific theories. So a scientific law summarizes a lot of observations, a lot of consistent observations, and it can be used to predict future observations. So from Lavoisier's experiments burning things in closed containers, he came up with the law of conservation of mass. It says that in a chemical reaction, matter is neither created nor destroyed. Another law, scientific law you might be familiar with, is the law of gravity. So the law of gravity allows us to predict what's going to happen. If I hold this Sharpie marker out and I let go of it, what does the law of gravity predict will happen? It's going to fall. And it does every single time, because the law of gravity works really well. Does a statement of the law of gravity explain why something falls towards the center of the Earth? It doesn't. And in fact, scientists are still kind of wrestling with what exactly is gravity. So scientific law summarizes past observations. Scientific laws are also experimented upon, and sometimes we find out that there are some things about them that are wrong. Young children are continually experimenting with the law of gravity, but it always works. Unlike state or federal laws, which you can just choose to disobey, you cannot choose to disobey scientific laws. You can't say, I'm not going to be subject to the law of gravity today. Just not going to do it. You can't do that. So laws describe how nature behaves. And then there are theories, and theories arise from the hypotheses. So the theory explains why those observations are what they are. It's a model for the way nature is. It explains not just what it does, but why. So this whole idea of the law of conservation of mass was explained later in the 1800s by John Dalton's atomic theory. So his atomic theory, explaining the law of conservation of mass, says that matter is composed of small indestructible particles called atoms. Atoms are like Lego blocks. You can't break a Lego block with your hand. And these particles merely rearrange in a chemical reaction, and that's why the amount of mass stays the same. So if you start out with 100 Lego bricks and you build one thing and you take them apart and you build something else, you still have 100 Lego bricks. They're going to weigh the same. That's the idea of atomic theory. Theories are also validated by experiments. An interesting idea, and it's actually somewhat troublesome, we can never prove anything to be correct. You can prove something to be incorrect, but you can't prove it to be correct. So all we can say about a good theory is that to our best of our knowledge, it is correct. No one has been able to disprove it. Scientists are skeptical and curious people, and so we keep testing, and as new technology and new ideas come along, we take those and apply them to old theories and see if we can disprove them, because that would just be fun somehow to mess everything up. So theories are explaining, laws tell what happened. Both of these can be used to predict future behavior. A well-established theory is as close to truth as we can get in science. So here is a sort of a picture of the scientific method. There's a lot of going around in circles in the scientific method. And you can actually kind of start almost anywhere. Well, let's just start here. An observation. Observation leads to a hypothesis. I think this is why this is happening. And then you test it through an experiment. You can confirm the hypothesis, or you may need to revise it, and then you're probably going to go around this circle many times, testing that. Observations can also lead to laws, like the law of gravity. And then those laws can also be tested. A good hypothesis that's been tested a lot can turn into a theory explaining nature or the behavior of matter, and that theory is also subject to testing by experiment, and it can be confirmed or revised. Anybody have any questions? I have so many questions about this computer. So here's a conceptual connection. In your textbook, there are some examples, and those are usually involve calculations of some sort. And then there are conceptual connections. And so some of these I've chosen to pull into lecture because I think it helps us to just stop and say, am I getting this? So think about the answer to this. Which statement best explains the difference between a law and a theory? We have three choices here. A law is truth. A theory is a mere speculation. Choice B, a law summarizes a series of related observations. A theory gives the underlying reasons for them. Or C, a theory describes what nature does, and a law describes why nature does it. And the answer is B. C is very tempting, but C is exactly backwards. Laws describe what, and theories describe why. So, any questions?